You are viewing one of 10 modules developed through a project funded by Geoscience BC focused on direct use geothermal resources in British Columbia. This follow-up project was carried out between August and December 2016. The project was executed by Tuyaterra GeoCorp. These modules were developed from the Direct Use Geothermal Resources Roadmap published by Geoscience BC in June 2016. They incorporate additional educational material that were developed as part of the current follow-up project. The voices you will hear narrating the module are myself, Catherine Hickson, and my colleague,
Juliana Proenza.
This module, we're going to cover economic considerations of the geothermal development. So for an outline, basically this module is going to cover everything that you need to think about, not necessarily know about, but certainly need to think about to go ahead with your geothermal development. And by thinking about it, what you need to know is all of these various aspects will require some kind of an input when you start working on your financial model. So there are several phases to your development. We need to identify that, in fact, that there's a resource there, and in that identification, you're going to have to permit it, you're going to have a lease, and you need to have a business model once you know what your flow rates are and what your temperature is. Then, and that, of course, we're going to deal with under the exploration phase, is finding out what's down there, how hot it is, and how much of it can we bring to the surface and usefully use. Then we're going to have to design and construct whatever that development is going to be, whether it's going to be a greenhouse or a spa or something like that. But there's many other aspects that we need to take into consideration, not just what the commodity is, but what do we need to build to service that business model that we've created. And of course, once you've built it, then we need to operate it and maintain it. So all of these things you need to take into consideration when you're doing your geothermal development, when you're working at your pre-feasibility, and then finally at the feasibility, and then going on to construction. So the inputs that we need are, we have to know what our resource is. We have to know, what are we going to do with it? What kind of demand is going to be needed for what we are envisioning? If it's a small pool, it will have a much lower demand than if it's, say, a greenhouse complex that will require high flow rates and temperatures of a particular level. Then, once we understand what it is we're going to do, then we have to do the economic analysis, and then the surface assessment. What do we need to do? How do we need to build this? What's it going to cost us to put this all together? And often we use various computer programs. One is GIS, which is a Geographic Information System, and a Geographic Information System is a way of handling all of the enormous amount of data which is produced in that exploration and assessment phase. So, Juliana, do you want to talk about this a bit more?
Yeah, so this slide really just expands on the various factors that you would be considering under each broad subject, like resource assessment, what's the demand assessment, and what's the surface cost assessment. We've included this slide that's actually taken from a geothermal workshop that was held in 2015, where they were discussing GeoFires, which is one particular software that evaluates a resource in terms of its economic viability. And so these are all the different types of data that would be incorporated into evaluating whether or not a project is economically feasible.
So moving along, this chart gives you what are our costs and what are the project risks. I think it does this in a quite an effective way. And what you see by moving basically from our pre-survey, so we have an idea on the far left-hand side, to on the right-hand side, that idea is come to reality, and we are constructing, we have a plant or a project that we've constructed, and now we are operating and maintaining it. So as you move from left to right, the idea doesn't cost you anything, but obviously constructing and then maintaining that, whatever that might be, that project is going to cost a fair amount. So that's why you see the rising costs as we move from left to right. And of course, the other thing that happens as you move from left to right is the risk of your development project failing goes down, because we have more and more information, you're more and more advanced, and so you have an end point that is easier to reach. Now, what is important is that kind of crossover line, and that crossover where our risk and our costs the costs start to escalate and the risk goes down, is the drilling phase. Drilling is very expensive, depending on how deep and the diameter of the well that you're going through. So for power production, drilling is an incredibly costly part of the process. One of the good things about direct use is that we typically drill fewer wells, not necessarily as deep or as wide a diameter as you might use for power production. So the costs are lower overall than for a power production project. Now, the cost of money is very important. So this is just another way of looking at our project. So now we have year across the top, and at the bottom we have something called equity financing and debt financing. And then in the vertical axis, what we're doing is the same things we've just spoken about. We're developing our project. We have an idea at the beginning. We then need to figure out what it is we're going to do. We need to drill it. We need to get some project financing, and we need to build it. That red line is very critical. In power generation, that red line indicates when you can go to the bank and ask for debt financing. On the left-hand side of the line is what we call equity financing. And equity financing is your shareholders of your company, or if it's a government, tax dollars are needed to move that project forward. Once we can go to the bank, then we can get debt financing and we move the project through to fruition. In geothermal, unlike in wind and solar, that red vertical bar is set at a very high rate. You may have to spend many millions of dollars in order to drill and prove that you have a resource before you can go to the bank for debt financing. It's that red line and that difference between the equity financing, having to raise the money either from shareholders or taxpayers, and when you can get it from the bank, that is a make or break issue for the company. And it's very hard to raise capital sometimes in today's market. But if you can do it, then geothermal ends up being a very cost-effective way to produce power. So what we call that is bankability. So that red line is the point where a bank will accept a loan or accept your project and give you a loan to keep it going. In order to get to that state, we need to do initially a pre-feasibility study and finally a feasibility study. We need to have a business model that takes into consideration what is all of this going to cost and what do we expect to make in terms of revenue from what this project is going to finally be when it is completely finished. And we do that through a financial analysis. And this is typically done by somebody with a skill in that particular area that takes into account all of the costs that are going to be part of the development of the project and then looks at what the revenue is downstream. Now, just as a little bit of reality check here, this is specifically for power development. And if we look at projects within the oil and gas sector or within wind, typically those projects for oil and gas take 3 to 5 years. And that's from the time we have that bright idea to we've built we've built either an oil plant or a gas turbine, or in the case of wind is even faster. 1.5 years from that idea, getting our basic data, to having a wind power plant producing electrons. Against that, let's look at geothermal power. So the huge advantage of geothermal is its base load. Against oil and gas and wind, what we have for geothermal is a base load. So base load with a very high level of availability. Basically more than 98% of the time that power is available. So this is very important if we look at other renewables. Other renewables, essentially with wind, you don't generate power unless the wind is blowing. Solar, you need to have sun shining down. So in those cases, the renewables have to be able to store power. And that's a big technological move that's happening right now within renewables. But going back to geothermal, we have that. That is built into our resource. It is 24/7. It has a very long lifespan, decades, 50 years, potentially 100 years or more. But the cost is very high. And remember, I talked about the equity financing. That equity financing has to come from shareholders or from government. From the point where you have been able to drill and prove your resource to actually producing electrons can take significantly longer, because you're looking for that debt financing from the bank. So what you see here is a number of projects, and what is shown is they've had a discovery well. So they've used their equity financing to drill a well and prove there is a resource there, to the length of time it has taken from that point to be producing electrons. And you can see it can be as rapid as 3 years, and in other cases, such as El Tatio in Chile, there is not yet electrical generation. So this is just a note of caution. You need to work hard on your financial model. You need to understand your system very well, and you need to make sure that your funding is sufficient to move your project forward. So in our financial model, we have to take into account a number of different factors, and one is the capital costs. So capital are split usually into these 3 different pieces. That early stage exploration, our geology, our geophysics, we're test drilling, and we're doing our environmental work. From that point, then we have to develop our field. So we're going to be building drill pads, we have to have access roads, and we're going to be testing those wells. So that's usually considered as a separate component in our capital costs. And then downstream installation. So now that we've been doing our drilling, now what are we going to do to capture that energy? What do we need? Is it a transmission line? Is it pipelines? What do we need to do to create our installation? Now, we have to remember there are indirect costs. So in the case of buying a piece of equipment, we have a physical object, but we have to remember that that physical object requires a lot of different costs behind it. You had to engineer it to get it, to figure out that it is the correct piece of equipment. You need to supervise that installation, and then you need to commission it. Things like spare parts need to be taken into consideration. And then obviously we have to have our permits. Those permits are both land use as well as use of buildings. And in some cases you need permits to actually produce your power. And there's usually insurance. So these are indirect costs that we have to remember are part of our financial models. And, you know, a key feature noted here is that every project is different. So what you need to do is make sure that you understand what your indirect costs are for your particular projects. And as I've already mentioned, power generation usually has higher indirect costs than a direct use project. And this really gives you an idea of what it's going to cost you in the long run. So this is the maintenance. So we've built our system, and now we need to maintain that system. And you can see that there's a very wide range here. The ground source heat pumps have a wide range, and that depends on whether or not we are dealing with essentially what our project parameters look like. But in general, a binary plant, if we're talking about power, will cost you more than a hybrid flash and binary plant. So this just needs to be taken into consideration that the capital costs vary, and ground source heat pumps are usually on the cheaper end, with power systems on the more expensive end. And as we go forward, we've now built our whatever it is, we've built our project. Now we need to operate and maintain it. So typically, the operating and maintenance costs are considered as a percentage of the capital costs, and that's typically about 3 to 5%. And in this analysis, you need to think about how many people do you need to operate this? What kind of spare parts? Do you need a lot of consumable parts? What's your maintenance going to be? And maintenance is a very important aspect of power production, as well as direct use. And remember, in previous modules, we were talking about the chemistry of the fluid. So if your chemistry is benign, then your maintenance costs can be quite low. However, if you're dealing with a very corrosive fluid, or a fluid that produces a lot of scale, then your ongoing maintenance is going to be much higher. And finally, revenues. What money are we going to be able to make from this particular project? And of course, this is what the bank wants to hear from you. How are you going to convert that energy, whether you're going to measure it in joules or BTUs, how are you going to take that energy and convert it into money to pay back your loan? So some of the things to consider is the resource park concept, that if we want to take every bit of energy out of that fluid and put it to some use. And the more uses that we can apply that energy to, usually the more economical any individual project or part of that project is. So we need to understand, what's our break-even point? What do we need to do to make this project work?
So this chart showcases what the potential direct use and ground source heat pump capacity growth scenarios are, starting from 2010 up to 2050. And although this is, a graph that is about 5 years old now, what it's really showcasing is that the growth of direct use globally is really being driven by ground source heat pumps. So that's why we've included GeoExchange, another word for ground source heat pumps, in some of our modules to really represent that the geothermal direct use spectrum includes ground source heat pumps. And as projects are developed, there are more and more projects that are utilizing heat pumps in conjunction with direct use applications. So you may still be drilling deeper into the ground, utilizing a water resource, but then to further increase the economic viability of a project, you may be including ground source heat pump systems to increase the efficiency of that system as you decrease the fluid temperature to the lower end of the spectrum. This is a table that's showing some of the differences in economic considerations that you may be looking at when comparing direct use versus GeoExchange systems. So, for example, the availability of the geothermal resource for direct use usually requires an anomalous heat flow area, but not necessarily always. If you've got aquifers that are 500 or 700 meters that are known, that may not be manifested at the surface, but you may have that information through drilling for other means, and you may realize that, hey, there's a geothermal resource at depth here. Conversely, for ground source heat pumps, these can be installed pretty much anywhere. So the constant temperature of the ground at 5 to 100 meters is consistent throughout the year, pretty much everywhere in the world, excluding maybe where there is permafrost. So in terms of types of direct use and ground source heat pumps, there are different configurations for ground source heat pumps that would result in more expensive systems, such as vertical borehole drilling. And for direct use, similarly, if you've got a system that is manifested at the surface, you know that you won't be drilling very far to extract that resource, but you would likely be drilling deeper, and so your costs increase considerably the deeper you have to go. In terms of end uses for direct use, the higher temperature resources could be used for industrial processes up until electrical generation, and using those combined in combined heat and power systems. And in terms of the limitations, well, for direct use, the quality and quantity of a resource really determines the limits of the end use. So really understanding your resource at the beginning to advanced stages and knowing the flow rate and temperature limits, that really drives how your system could be used at the end use. And for ground source heat pumps, they're actually very flexible. They can be sized for the smallest residential need to the largest commercial facilities. And so that really has been the driver for ground source heat pump usage, where for direct use, you really need a dense populations to maximize the economic value of a direct use potential resource development. And then we've got some examples in terms of lifespan and permitting. So for permitting ground source heat pumps, it's usually minimal and reflected by zoning bylaws. And for direct use, it really varies provincially, but in BC, you would be including the Land Act and the Water Sustainability Act in order to utilize that water resource under 80 degrees. And if you've got water greater than 80 degrees, you have the added complication of going through the permitting process under the Geothermal Resources Act. So factors that increase favorability for project economics are essentially whether or not you have to do a lot of legwork for non-invasive exploration, although this is usually the less expensive part of a project. If you have a project that this work has already been done on, you are one step ahead of the game. Another factor that is favorable is whether or not you've got existing infrastructure. So is there a previous or an active mine nearby? Are there nearby communities? Are there existing roads or oil and gas fields? This existing infrastructure can really play a big role in terms of decreasing the economic costs of a direct use project. Other factors that you have to consider are the potential end users and possible applications that are already in place. So again, you're one step ahead of the game if you've already got potential end users involved in the project development project, and what those possible applications could be in order to connect to that geothermal resource. For example, is there farming nearby? Are there greenhouses? Is there industrial processes that are facilities nearby, like a pulp mill or lumber drying? Is there potential for district heating or cooling for a neighborhood or a commercial area? Is there an aquaculture facility nearby? So those are all things that can be taken into account, and if these market end uses exist, then the economics are even more favorable. And again, just hitting home the cascading uses for that same geothermal fluid. So at the higher temperature, you could be using it for end-use applications that need that temperature. But as the fluid is going through that process and some of that heat is extracted, at that lower temperature stage, you could still be using that fluid for another process that doesn't require as high temperature, and et cetera, et cetera. And so this cascading use for the same geothermal fluid is really key for increasing the favorability of project economics. In terms of fuel savings, so this slide showcases what the fuel savings are when you compare geothermal to other conventional heating systems. And in this case, this is geo-exchange systems. So we've got geothermal at the bottom there that's representing the lower costs in terms of annual heating costs. So not necessarily the upfront costs in order to deploy the system, but once the system is deployed, this is what your heating cost is year to year. And while you're evaluating project economics, it's really important to understand what that communities or the industrial areas nearby are using in terms of energy that you would be replacing with that geothermal system. So again, for a residential home, about 80% of a home's energy use is for space and water heating, and that number is a little bit lower for commercial industrial use, but it's still a significant number, which is about 63%. So here we are highlighting the different types of direct use applications and what the capital costs are, what the operating and maintenance costs are, and then what the total costs are per unit, per kilowatt hour, and per kilowatt year. So we've got here residential space heating, and then greenhouses, aquaculture, and also comparing those costs to geothermal heat pumps. And these charts are examples from the United States, and so here we are comparing direct use to conventional heating. So as we compare geothermal costs for heating different end-use applications, what would be conversely the cost if you were using natural gas or diesel or electricity to provide heat? So here we have included something that is quite an innovative project that is currently being developed in the States and has recently been given quite a bit of granting money. And so this is a study that was based on a PhD thesis, and essentially what it's showing is that in the northeast of the US, which you would normally not think of a high geothermal resource area, they have a lot of oil and gas data information, and they can evaluate this data in terms of deep drilling and whether or not this can be used for dense areas in the northeast of the US, like New York State, for example, and provide heat for university campuses or small communities or dense parts of cities. And so a demonstration project that is going ahead is at Cornell University, and essentially they are going to be evaluating the economic viability of deep direct use. So essentially it's the same idea utilizing a geothermal resource, but it's drilling deeper than you normally would. So ideally you would be drilling 1 or 2 or 3 kilometers deep. In this case they may be looking at drilling as deep as 4 or 5 kilometers, where the geothermal resource is much more prevalent in certain areas where you wouldn't necessarily think is geothermally active. So this example essentially showcases that using today's technology and possibly utilizing deep direct use, if it were a mature technology, how would the cost decrease? And comparing those costs with 3 different resource grades. So if you've got a geothermal gradient that is 30 degrees per kilometer, compare that to 70 degrees per kilometer, obviously the economics would be more favorable for a higher geothermal gradient, and the more mature the technology, the higher your economic viability is. So one of the other economic considerations in Canada is that we do have 2 tax classes that represent tax incentives for geothermal, and essentially it allows you to include geothermal equipment used for direct use applications, geo-exchange, and geothermal power production as part of accelerated capital cost allowances. So there are two classes, 43.1 and 43.2, and the difference between the two is that 43.1 is 30% accelerated capital cost allowance, and 43.2 is 50%. And in order to qualify, you basically, it's all of the equipment that is utilized within, in this example, geo-exchange system. So the heat pumps, the piping, the equipment that's used for energy conversion, the equipment that may be used for energy storage. All of these different equipment can be used under these classes for accelerated capital cost allowances. And it goes beyond just geo-exchange. It can also be used for direct use. So in this case, we've got district energy systems, and there are various different ways that you can provide heat for district energy systems, and one of those is geothermal. And so all of the different equipment utilized in that system are also eligible for these tax incentives. And going even further, for geothermal power production, you also are eligible to utilize some of the equipment that's used for these systems for these tax incentives.
And just to add, what's important about those tax considerations is they help your modeling. And what these incentives do is make your potential project more favorable. And that is important when you're going to the bank and trying to get debt financing. So these are important considerations that need to be taken into your financial model.
So there are several tools that can be used for economic modeling, and like Kathy mentioned earlier, these would typically be done by experts that specialize in geothermal systems and economic modeling. So GeoFires is quite a recently developed software that was developed as part of a PhD thesis. And essentially it is evaluating the economic viability of the production of heat and electricity. It also has the capability of evaluating either standalone and together. On the electrical generation side of things, you have an economic modeling tool called GETEM, which is Geothermal Energy Technology Evaluation Model. So essentially these systems have various different inputs that can be included. And for the example of GeoFires, we've got 96 input parameters, and these input parameters cover all of the information that you would have gathered in the early and advanced stage of exploration that characterize your resource. And then as you progress, all of your engineering parameters, your reservoir model parameters, and then all of your different economic parameters, such as your capital costs, your operating and maintenance costs, and then any parameters that you may include to optimize the system. Another economic modeling tool that's available and has actually been developed by Natural Resources Canada and used internationally for geothermal systems as well as other renewable energy technologies is called RET Screen, so Renewable Energy Technology Screening Tool. And essentially what it is a clean energy management software system, and it can be used for energy efficiency as well as renewable energy and cogeneration project feasibility analysis, and includes things like geothermal power production, geo-exchange, direct use, as well as micro hydro projects and other alternative technologies. And it also allows for ongoing energy performance analysis. So you could use it to evaluate how is your system performing, what can you do to increase its efficiency. It's a tool that is based in Excel, and it allows you to use different data that is already incorporated into the software, such as climate data. And it allows you to compare the system that you are evaluating to conventional heating, for example, in our case. So this is just a screenshot that showcases what the different inputs may be. So in this case, you can compare it to natural gas or biomass. And for a heating process, you would be providing inputs for example, what the heating load of the building is, and what the domestic hot water heating base demand is. And all of these different economic parameters would be put into the evaluation software, and then you would get an economic summary at the end. It also includes things like emissions analysis as well as the financial analysis. And it can be used for a single unit geoexchange system or a large geoexchange field, for example.